Okay, thank you. Okay, so I will get started. Maybe just to start things up a bit slowly, we'll do a quick recap of what we covered last time, and then we'll jump into new stuff. Um, as before, if you have any questions, please feel free to interrupt me at any point. So let's remember where we were. We were
I
trying
don't
to
know why
set
there's
up.
a problem. Hi, maybe we can test the audio. No, he's not muted. It shows there. I think it's our end.
Can the other people on Zoom hear me?
Hi.
Yes, on Zoom
Yes.
you are audible.
Yeah.
Okay.
Hello.
Hi.
Audio. We can't hear the speaker. Can you say something, please, Sivaraman?
Hi.
No, it's still not working. Now, could you please try now?
Yeah. Can you hear me now?
Hi, Sivaraman. So we are ready to start. You can just.
Okay. So this works?
We're good.
Okay. All right. So let me just repeat what I said. So I'll start off just to get us warmed up with a recap of last time. As usual, please feel free to stop me at any point if you have questions. Okay, so last time we started setting up this framework of optimal transport. So roughly we started with this premise that, okay, I'll hand you two distributions, mu and nu, and we want to transform mu to nu, and we want to minimize some specified cost. So this was the basic template of the problem that we wanted to solve. Monge formulated this problem originally, and he did so by saying, okay, let me first define what a transport map is. And we will use this notation that T pushes forward mu onto nu. To mean, maybe intuitively at least, you should first think of it this way. If I give you a random variable with distribution nu and you pass it through this map, then you obtain a random variable which has distribution nu. Right? So that's what's written over here. And okay, once you define transport maps, there are ways of moving random variables with one distribution to the other. Then you can say, okay, what is the transport map which has minimal cost? And so I will specify for you some cost. And you look at the average cost of your transport map. That's the thing over here. And then you say the optimal transport map, this will be the target. This is the thing that we're after, is the one that minimizes this expected cost over all valid transport maps. So it moves mu onto nu and minimizes the average cost. And then we discussed that this maybe is not a very nice optimization problem. It has a nonlinear constraint. It's not convex in any sense. And even we also saw counterexamples. There aren't always solutions to this problem. So then we talked about Kantorovic's formulation. So Kantorovich said, okay, forget about maps. Let's talk about couplings. Couplings are joint distributions on these two spaces, which have first marginal mu and second marginal nu. And then he defined what we would call the OT coupling. It's the coupling that has minimum cost. Right? So that's this object gamma 0 over here. And um, this we remarked was a linear program. It's a very nice optimization program. If you look at it, the constraints that define a coupling are all linear, and the objective itself is a linear function of this variable gamma. We use this then to define what are called Wasserstein distances. So Wasserstein distances are the cost of Kantorovich's minimum coupling. Particularly, we usually think of WP distances, which are you take the cost to be the Euclidean distance raised to the pth power, you find the value of Kantorovich's program, which is how much does it cost to actually move mu onto nu, and this defines a metric between distributions. It's a very nice metric between distributions, and we'll explore it a little bit today. And so, okay, so once you set up Kantorovich's program, you can define Wasserstein distances, which are just the cost of the best coupling between the distributions, and that defines a metric. And maybe this is just a more general way to think about the OT framework. It gives you a way to lift a metric on some space. So you started off with a metric between points on your space. That's the Euclidean metric. And OT gives you some way to lift it up to a metric between distributions defined on that space. So, and it does so in a way that respects the ground metric. So you have some ground metric, and optimal transport will tell you how to define a metric on top of them for distributions defined on that space. Okay. And then we said, okay, what is the relationship between Monge and Katowicz's problem? And one relationship is Brenier's theorem. So what it says is, suppose you work with the squared Euclidean cost. This is one of the cases that we'll focus on a lot. And suppose that I give you distributions that have two bounded moments, and the first distribution is absolutely continuous. It has a density with respect to the Lebesgue measure. Then Brenier's theorem will tell you that Monge and Katowicz's problems are very strongly related. So Monge's problem has a solution. We'll call it T0. That will always be the gradient of a convex function. So phi0 is some convex function. Its gradient will be the transport map. So this is some way of saying the transport map has some nice monotonicity property. And also Kantorowicz's program has a solution which is exactly, you can read it off from Monge's solution. So it'll be a coupling of the form x t0 of x. So you should imagine it's a coupling which is supported on the graph of a function. It's a degenerate coupling in some sense. It says take every point x and move it to the point t0 of x. That defines a coupling. Okay, so we also briefly saw that you can reverse all of these things. That is, if the distribution nu is also absolutely continuous, then you can define the reverse map from nu to mu. And in this case, it will take the form that it will be the gradient of the conjugate of the original function. So the gradient of some convex function pushes you over, the gradient of its conjugate will pull you back. Okay, then we started talking about duality. And this is where we roughly ended. So duality, at least in the discrete case, we just derived the dual. It's an LP, so it's easy to do. So you start off with Kantorowicz's program. In the discrete case, it says find a coupling, gamma. So you minimize over gamma, which minimizes the cost. That's the objective. And the fact that it's a valid coupling is encoded by the set of linear constraints here. So we derived the dual and we arrived at this problem. It looks like this. It says maximize the sum of alpha I plus beta j, subject to the constraint that alpha I plus beta j pointwise should be less than the cost for moving from I to j. And then we interpreted this dual, and we'll spend some more time with duals of the OT program today. Okay, so that was the recap. If anyone has questions, maybe now is a good time to ask. Okay, so then I'll tell you quickly the outline for today. We'll start off with, I'll tell you a little bit about a different way to think about the optimal transport setting. It's called the polar factorization theorem. And then we'll spend most of today on duality. We'll derive some of these very useful and basic facts about the dual of the optimal transport program. And then we'll start talking about the setting of statistical optimal transport. We'll talk about what are the basic questions. And then maybe if we have some time, we'll get to this last topic, which is how do you estimate the optimal transport map from samples? Okay, so let's start off with the polar factorization theorem. It's another result of Brenier's. It just is another intuitive way to um, to define the optimal transport map, but maybe not necessarily Monge's way of doing it. And for some, maybe this is a more intuitive way of doing it. So let me explain what the idea is. So here's the idea. So what did Monge tell us? I mean, sorry, what did Brenier's original theorem tell us? This is also a result of Brenier's. So his original result said the following. Suppose I give you that you're working with the quadratic cost and I give you some pair of measures and mu is absolutely continuous, then there is an OT map T0 and it's equal to the gradient of a convex function phi0. Right. So in this same setting, Brenier proved a different result. It just says that if I give you any other valid transport map, so any other valid transport map, it doesn't need to care about the cost at all. Can be always decomposed. It has a factorization in the following form. So let's suppose I give you a valid transport map T, then T can always be written as the composition of two maps. So one of them is this map T0, and it's composed with another map S, where S is a measure preserving map. So S is just a map from mu to itself. S is a measure preserving map. So that is, it maps mu back to itself. Okay, so this is the statement of the theorem. It says that if I give you any valid transport map that moves mu onto nu, you can decompose it into two maps. One of them just takes mu and shuffles it around, and the other one takes the output of that measure preserving map and then transports it to the distribution nu. So this is a different way. So it doesn't invoke the quadratic cost itself. It just says one way to have defined the OT map is to say, take the polar factorization of any map and then just identify the piece that's not the measure preserving piece. That will be the OT map. It will be optimal according to the quadratic cost. So you should think any other map does something suboptimal. It first moves some mass around, but it maintains the distribution. And then it does the optimal thing, which is you move from mute back onto nu. Okay, so this is just a nice different way of thinking about it. You can think about the optimal transport map as the one for which S is the identity. The identity map, then T will be equal to T0. This is somehow some way of thinking about what the OT map is. And the reason why it's called the polar factorization theorem is it's a generalization of polar factorizations of matrices. So again, this is a fact about matrices that you can take any matrix M can be written as a, I guess, a PSD matrix times. So this is a PSD matrix. Well, okay, I should use different notation. So, let's say a PSD matrix times an orthonormal matrix. So that is. Right, so this fact is somehow generalized by this. The way you should think about it is if I thought about transporting Gaussians, right? So suppose X had a distribution which is normal with zero identity, then M times X also has a distribution which is a normal with some mean, some covariance matrix, doesn't matter. Yes. Right. And so now you can say, what is the OT map between these two distributions? The OT map will be you decompose M as some piece P times some orthonormal piece, and this will be the OT map between them. This is the OT map. And then there'll be some extra orthonormal piece, which is the measure preserving piece. Right? So if I take an orthonormal matrix and I apply it to X, I still get out as the output a Gaussian. And so this is just saying this decomposition for the case of transporting Gaussians recovers for you the polar factorization theorem, but the polar factorization theorem holds much more generally. Is everyone okay so far? And maybe it's okay. You can think about phi of x here as x transpose px divided by 2. And so the OT map T0 is this is a convex function, and the OT map T0 is the gradient of this convex function, which is just px. And so, yeah.
So here in this polar preservation theorem, the cost function could be anything.
So it doesn't involve a cost. I'm just saying if you think about a transport map, any transport map, this doesn't invoke a cost at all.
Right, I
It can be
get it.
decomposed according to the optimal transport map, according to the quadratic cost, and another piece.
I see.
Very good. Other questions?
Just a small clarification. This
Yeah.
holds under the same assumptions as Brainier's theorem, right? That mu is
Mhm.
absolutely continuous and all. Okay, okay. Yeah, thank
Yeah.
you.
Okay. So good. So then let's go back to duality. So let's I'll write out again this the Kantorovich dual in the discrete case, and then I'll tell you what the generalization will be when you apply it more generally. So the Kantorovich dual in the discrete case looked like this. And subject to the constraint that alpha I plus beta j is less than Cij. So more generally, you could have done this. There was nothing specific to the discrete case that we nothing that we did was specific to the discrete case. In the continuous case, for instance, you would just have infinitely many constraints, but you can still formulate the Lagrangian in the same way. You just multiply by a function. So you multiply each constraint by a function, and then you put it together in the same way. So the general dual will look like this. So the general Kantorovich dual. So this is a case of infinite dimensional duality, would just be the following thing. You maximize over two functions f and g. Maybe, okay. For this to actually make sense, f has to be an L1 function with respect to mu, and g has to be an L1 function with respect to nu. So you maximize this, and so what is this expression and this expression? It'll work out that the correct generalization will be the integral of f d mu plus the integral of g d nu. So that is, in the discrete case, we took everything to be atoms of mass 1 over n. In general, it will be these two objects that will form the objective. And the constraint will look the same as it did before. It just says f of x plus g of y should be less than the cost for going from x to y. Okay, so this is the Kantorovich dual in general. Let me pause for a second and see. So I'm not going to actually derive it. It needs a little bit of care, but you should think of it as somehow the analogous thing that we did in the discrete case will exactly map the first dual to the second one. Everyone okay so far? Okay, so let me just make some remarks. So one of them is something about strong duality. So in an LP, I guess strong duality essentially always holds. Here, provided the cost C is lower semi-continuous and bounded below. So satisfy some mild regularity conditions that in our examples will always be satisfied. If your cost satisfies these, then strong duality will hold. And maybe for us, this will just mean that at least as long as our cost satisfies this, this is some vague intuition, just that if strong duality holds and it's an LP, then you should expect that there will be some relationship between the primal solutions and dual solutions. And we'll see what those relationships are today. Okay, so let's make some structural remarks about the dual. So we're going to start just probing this dual in two special cases, the case where the cost is the Euclidean cost and the case where the cost is the squared Euclidean cost. So those will correspond in some sense to W1 and W2, which are the two famous examples. So, okay, so let's make some structural remarks. So let's do the case when p equals 1. So the first thing to generally observe is that I can um, just maybe intuitively just think of the case. So I fix an f, and then I try to say, okay, what is the optimal g for this program? Right? So let's say I optimize over g. It'll turn out that g will have a specific form. It will be what is called the C transform of the function f. So what does that mean? So I'm trying to make something like the integral of g as large as possible. And the constraint on g is that it has to be smaller than, so these are the constraints on g. Right? So we know that g of y should be, it has to be less than f of x. Sorry, has to be less than c xy minus f of x. it has to hold for every x, this constraint. So it makes sense to try to define it. So this would be the largest possible value that you can put in, right? And so this will be, we'll just call this the C transform of f. And so this is the C transform of f at the point y. And this terminology will make sense in a second. But you can see that there's some sort of conjugate relationship between f and g. So if you should imagine in your head, I fix f and say, what is the best g that I can create? It will be exactly this value. And so you take this value and you define it to be the C conjugate. And so it just says that, okay, if I fix f and optimize over g, the optimal g will be the C conjugate of f. Is everyone okay so far? So this statement is true generally. So now let's talk about the case when p is equal to 1, right? So this is the case where the cost is the norm of x minus y. Okay, so we'll check some properties. So let me tell you why we're going through this exercise. So we will check two properties and so the first one is that the C transform of any function is always going to be 1 Lipschitz. So where for this particular cost. And the second thing is that the C transform of a 1 Lipschitz function will be minus the function. Okay, I'll tell you in a second why we want these two properties, but let's say these two properties are true. Then we will be able to derive some nice structure out of the dual. Right, so let's for now just assume these are true and then we'll come back and verify them. So what am I going to do? I want to stare at this dual program. I'm going to imagine iterating this a couple of times. I'm going to take a function f, fix it, optimize over g. I will get some function out, and then I will go back and optimize over f, and I will repeat it one more time. Okay, so this will keep increasing the value of this thing. So you can instead think for a second of maximizing over f, which is an L1 mu function, the integral of f. Okay, so maybe I'll also remark that if you take, when you define G to be the C transform, you can just drop the constraints because all the constraints are naturally satisfied by the C transform. It's okay. Let me do this. So you can imagine that I can sort of iterate my intuitive argument. I'll start with some f. I will take its C transform, take its C transform again. That will be the optimal f. And then I will take its C transform one more time, and that will give me the corresponding optimal G. Okay? So let's say I can do this, and this will only improve my objective value. And so I can instead think about this maximization problem. So let me tell you why we're doing all of this. So one thing that we know is that this is a Lipschitz function. This is 1 Lipschitz. And this one will be the negative of that function. So this will be the negative of this. So you can equivalently think about the dual in the case when the cost is the L1, the W1 cost, that is this one. When the cost is this, we can equivalently think of the dual as just saying maximize over f, which are 1 Lipschitz, the integral of f d mu minus the integral of f d nu. Okay, and so this is a famous expression. It's called the Kantarovich-Rubinstein duality. And okay, so now you can go through some steps to verify that strong duality actually holds, but this gives you the dual representation of the W1 distance. So if strong duality held, then it is the case that whatever I get from maximizing this dual program is equal to the primal cost, right? And that just tells you that the W1 distance between two distributions, mu and nu, is exactly the sup over F, which is uh, 1 Lipschitz, the integral of F d mu minus the integral of F d nu. Okay, so let me pause for a second and just see if we have questions, and then we will go back and quickly verify these C transform properties.
Hello.
Yeah,
Yeah. So, w- are you stating any theorem here that is saying the strong duality holds? Like, what exactly is the theorem or anything?
there is a theorem that says it, yes. In full generality, strong duality holds for this cost. So maybe the actual theorem is just that it's here. If C is lower, semi-continuous, and bounded below, and this cost is both of those things, then strong duality holds. I'm just saying, suppose that strong duality holds, what structural properties can we get out of the dual that tells us something interesting? And that's all. So I'm just assuming strong duality holds, and it does in this case.
I see. Okay. And how you are going from F and G to FCC and FCCC? Uh,
Yeah, so I'm just saying that uh, you the way to imagine it is I started with F and G. Uh, for any, if I gave you an optimal solution, it must be the case that G should have been the C transform of F. And similarly, so you have to have reached some fixed point of this kind of
I
like,
see. So assuming that everything is nice enough, you are making all these. Yeah.
so there is no additional assumption being made here. It is
So
just the case
strong
that,
duality holds is basically you are assuming that is the nice thing that I was referring.
yeah,
Yeah. Okay.
that's
Okay. Cool.
Yeah, and I'm just saying that, okay, when you think of this maximization over F and G, you can in your head think about, I don't know, fixing one of them, maximizing over the other, and then repeating this a few times and extracting some structural properties of the dual. And so a different way to say it is that if I solved the original Cantor-Wych dual, it will always be the case that there is a one Lipschitz F that maximizes this, and there is a corresponding G, which is also one Lipschitz and is the negative of F that maximizes it. So there is at least one maximizer of the form that I want. Okay, good. Other questions?
These assumptions on C for strong duality, are they arising out of some standard results on strong duality for linear programming, or
Yeah, I guess one could call them standard results, but yes, I mean, they are Kantorovic's results. It is an infinite dimensional linear program, so maybe there isn't, I don't know, there is not if you take a new optimization textbook, you will not find this kind of condition, but yeah.
okay, thanks.
Okay, so let me, okay, also just remark something if you haven't seen this
Hello.
before. So yeah, sorry.
I had a question. So in the expression of point number 3, you wrote that FCC. So you've given the P equal to 1 and all the assumptions. FCC is just F, right? So why did you, any particular reasons you just wrote FCC instead of F?
Uh, no, this is not the Fenchel conjugate, and it's not the Fenchel conjugate of a convex function. So it is not the case that FCC is equal to F. So nothing, I have defined the transform here. It If I started off with a function that's not one Lipschitz, FCC is not the same as F.
Okay, but since you started with the assumption that, so for all these theorems that you wrote, F d mu minus F d nu, the integral of that holds only when F is one Lipschitz, am I right?
No, that is so okay. So sorry, when I said L1 mu and L1 nu, those are not. I'm not saying they're one Lipschitz. I'm saying that the integral of F d mu is finite.
Okay, okay, okay. I see.
Sorry, I did not invent this notation, but it's not great notation when you're talking about one Lipschitz. I mean that they're L1 functions. So you didn't start off with the assumption that they're Lipschitz. You derived it somehow as a property of this duality.
Uh, did you mention the derivation? Because I don't get why they are one Lipschitz, F and
I
G.
will argue it for you in a minute, but maybe the intuition should be this fact that if I start with an F and I look at what is the best possible G, that will always be one Lipschitz. And then you can now imagine iterating this argument a few times, and then you will see that every function, both the functions have to be one Lipschitz. So for any F, the corresponding optimal G, I will prove to you, is one Lipschitz. And then you can conclude that both the functions have to be one Lipschitz as a conclusion.
Sure, thanks.
Okay, good. So maybe let me also try to give you some intuition about why this expression is useful, interesting, and so on. So this is saying that W1 is an integral probability metric. So let's take a 2-minute detour into this. So what is an integral probability metric? So more generally, you can try to define metrics which between distributions. So I want some notion of distance. I give you mu and nu. I want some way to capture a distance between them. One way to try to define them is to say, I'll define the distance between mu and nu to be the supremum over f in some hopefully big enough function class of the integral of f d mu minus the integral of f d nu. Right? This would be called an integral probability metric. You can put in some nice function class, and you will, if the function class is big enough, you will get out a metric at the end of this. And so W1 is an example of this, where the function class is the collection of one Lipschitz functions. But there are many other examples that we know that are interesting. So the total variation distance is also an IPM. And that's the IPM where, okay, so the TV between mu and nu, it also has a dual form like this. It's just the soup over F, which are, let's say, I don't know, let's say bounded functions. There's in this class, and then I say the integral of f d mu. So saying the way to define a distance between distributions is you take a bunch of base functions and say how different are the means of these base functions under these two distributions. That's the IPM. If I take this collection of base functions to be all bounded functions, then I recover the total variation distance. And similarly, there's another one which is called the maximum mean discrepancy. That's the MMD between two distributions is the supremum over functions which live in an RKHS. I will not tell you what an RKHS is, but let's just, so an RKHS is some class of functions which are defined via a kernel. That's a reproducing kernel Hilbert space. And then you say the same thing, the integral of f d mu minus the integral of f d nu. Right? So they all have the same sort of similar looking form. The W1 distance takes a supremum over Lipschitz functions. TV takes a supremum over all bounded functions, and MMD takes a supremum over RKHS norm bounded by one functions. And maybe the intuitive way to think about this is the unit ball of an RKHS is a very small collection of functions. So you can, this distance will be often not not very, it's not a very discriminative distance, so it will not be very large often. So you should think of RKHS unit ball is not a very big class of functions for a typical kernel. And then on the other hand, maybe the TV distance is taking a supremum over all bounded functions. That's a very, very big class of functions. And so at least if you cared about some statistical question, which is like, how well can I estimate the distance? The TV distance cannot be estimated from samples. On the other hand, the Wasserstein distance and the MMD can in fact be estimated from samples, but how well you can estimate them is reflected by this fact. So the MMD can be estimated very, very well, but maybe it's not that useful a distance often. On the other hand, W1 can be estimated less well, and we'll see some results of this form, but it is a somewhat more useful notion of distance.
So
And the
Shiva,
sorry, go.
can these distances, especially the W1 and MMD, can they be used in testing of hypothesis? The hypothesis is that the samples are coming from the same distribution.
Yeah, exactly. So that is somehow the most common use case of these distances is in some sort of either two sample testing or in one sample testing. So I give you a distribution and I give you some samples from the second distribution and I say, did they come from the same distribution or not? A reasonable strategy, at least roughly, is to estimate this distance and see if it's big or small.
I see. And what's the relationship between these three distances? Can one say something?
Uh, yeah, so you can always say that the TV distance is bigger than W1 just because this collection is bigger
Sure.
than this one. Other than
Also,
that, yeah.
so in the W1, F is also bounded by 1, or?
Uh, it's not. Yeah, so maybe I should be a little careful. Yeah, so over a bounded domain, W1 will be, yeah, so yeah, so okay. You can't sort of say something too general. Over a bounded domain, you can relate TV and W1.
Okay.
So over a bounded domain, a one Lipschitz function, you can just renormalize everything to start at 0, and then it cannot be too much bigger than whatever the diameter of the domain. And so you can relate it to the TV, it will be only bigger than the W1 up to that factor of B somewhere.
Right. Thanks.
Okay. Okay, so then let's
Hello.
yeah.
Small
Hi.
question. What is an integral probability metric?
It's kind of defined here. It's just you pick your favorite function class. So, and then I will define a metric, and all of them are called integral probability
Oh,
metrics.
got it.
They will only really be metrics if that function class is not trivial.
Got it. Thank you.
Yeah. Okay, so then let me just very quickly try to explain where this Lipschitzness came from, and it's just a property of C transforms, right? So let me just go back. I'm just trying to verify these two structural properties that if I take any function f and I take its C transform, it's one Lipschitz. And if I take a one Lipschitz function, its C transform will be its negation. So let's start off with the first property. So if I'm giving you any f, and I want to reason about the C transform. So what is the C transform? It is this thing, inf over x of the cost minus f of x. Right? So this is the definition, and I want to convince you that g of y is a one Lipschitz function. So you maybe should think about this as the pointwise infimum of an infinite collection of functions. So first I will convince you that each of those functions is one Lipschitz. So what does each of those functions mean? So let me define g tilde of y to be just, I fix an x and I look at, let's say x0 minus y minus f of x0. So this function, well, I guess, is one Lipschitz. This is easy to see, but maybe, okay, whatever. G tilde of y minus g tilde of y prime.
It's fine.
Is
The constraints
just
are-
and okay, so you can easily see that this is
So
yeah, so you can convince yourself that this is an infimum of a bunch of functions, each of them is one Lipschitz, and then you can check that the infimum of a bunch of one Lipschitz functions is also one Lipschitz. So okay. The okay, the conclusion, I'll not verify the second part for you, but the conclusion is just because you're taking the pointwise infimum of a bunch of one Lipschitz functions, the conclusion is that G, which is the C transform of F, is always one Lipschitz. Okay, so the second property is just suppose that f is one Lipschitz, then the C transform of f is minus f. So maybe I will instead prove that the C transform of minus f is f. This is just easier to prove. It's equivalent. But let's think about why this is true. So if I looked at the C transform of minus f, it is g of y is the inf over x minus y. Now it is plus f of x. So this is the C transform of minus f. So let me just convince you of two facts. So g of y must be less than, I can plug in any value of x that I like. So let me plug in x equals y. And so I see that g of y must be less than f of y. On the other hand, I know that f of y by the one Lipschitzness is always less than x minus y plus f of x. This is just by one Lipschitzness. So from this, I conclude that f of y must be less than the inf over x of the right-hand side. So that is, it must be less than g of y. Right, so I've somehow concluded these two properties hold. Here, I'm just take x equals y. And here, I'm checking that f is a valid thing to have put on the right-hand side, and therefore you get the reverse inequality. So maybe putting these together, you will just conclude that f must be g. That is, the C transform of minus f is in fact f. Okay. So
Quick question.
yeah,
Regarding property one, the proof of property one,
yeah.
you fixed the x naught for both y and y prime to be the same x naught. Why should that be the case?
It doesn't have to be. So I'm saying first, let's define a different function, which is the one without the inf. And I'm just proving to you that that function is Lipschitz. So I don't know, maybe you should think of this as I'm trying to say this is of the form inf over x of some function f sub x of y, where f sub x is one Lipschitz. So that's the only thing I'm proving to you. And then I'm saying that anything that looks like this, you can verify is always a one Lipschitz function. So I'm
I
saying,
see.
think
So
of it as a minimum of a bunch of functions. Each of those functions is one Lipschitz. Yeah.
okay, thanks.
Very good. So, okay, so maybe you can ignore some of these details, but what it's telling you is that the Kantorovich dual gives you some insight into the structure, particularly if the cost is the Euclidean cost, then you know that the dual objects both have to be Lipschitz functions. And in particular, that gives you this nice IPM representation of W1. And that's maybe the main takeaway for now. Okay, so now we will do something similar for the other cost, and we'll obtain some other structural properties for the squared Euclidean cost. Okay, so now we'll change gears, and now let's do duality for the squared Euclidean cost. So let's just remember our starting point. So our starting point is the general Kantorovich dual. Right? So we know that the dual is, it has the form, you take the sup over f, which is a L1 mu function, g, which is an L1 nu function of the integral f d mu. And now when we're working with the squared Euclidean cost, what we get is that f plus, so f of x plus g of y should be less than x minus y squared. And once again, we want to extract some structural properties of these things. So let me just make some remark about terminology. So the optimal F and G here are called Kantorovich potentials. And we will take the Kantorovich potentials, we'll transform them a little, and then we will get some useful things out of it. So let's suppose I take any function f and any function g. I'm going to sort of shift it a little bit and define some new functions. So I'm going to define for every f, it's in one-to-one correspondence with a function, I'll call it phi, which is just, so this is, and similarly for g of y, I can write it as the norm of y squared minus 2 times some other function at y. Right, so this is just, I'm defining phi and psi this way. Okay, everyone good so far? So I'm just saying, I wanted to inspect this dual. It'll be the convex analysis aspects of it will be clearer if I relabel these functions in some way. So I'm going to instead think about relabeling them and think about the dual as a function of this phi and psi instead. Okay, so let me just rewrite the dual now. So the dual will just be, I'm going to think of maximizing over phi and psi. The integral of f d mu will look like the integral of and then I get minus 2 times the integral of phi plus psi. Okay, so let me, sorry. Okay, so this is just the rewriting of the objective. And if I rewrite the constraint will be of the form that phi of x plus psi of y has to be at least so I will expand out the square. I will get a norm of x squared plus a norm of y squared. Those two things will cancel out. And I will get that this has to be at least x transpose y. Okay, and these two terms don't matter, they're just constants.
And I guess
So-
because of the because of the moment condition, they are bounded and we can remove them.
Yeah, exactly. So somewhere I have made the assumption that everything defining has bounded second moment, so they're just some finite numbers, I can throw them away. And so what am I arriving at? I'm arriving at this following dual instead. You can instead try to solve this thing. So up to this constant shift, it's the same dual, but you should think of it as it'll just be clearer what's going on now. So I'm going to take the inf over phi and psi, the integral of phi d mu plus the integral of psi d nu, with the constraint now that phi of x plus psi of y has to be at least x transpose y. Okay, so this is some sort of modified dual.
And then we can do the same trick, and then psi and phi have to be towards of each other the same way.
Exactly, perfect. So you're seeing ahead. So we can do the same trick that we did before, which is I want to think about what structure do these dual objects have. So I can imagine I'll fix a phi and say, what is the optimal psi? Right? So the optimal psi will be, so it has to be at least it has to be bigger than x transpose y minus phi of x for every x. So I can define it to be the sup over x of this thing. And this is just the Fenchel conjugate of phi. Right? So this is the usual Fenchel conjugate of phi. So what we're seeing is that, okay, the two objects in the Kantorovich dual for the quadratic cost have to be related. And rather than be the sort of C transform generally, for this cost, they are in fact related by standard convex conjugacy. So that is, this dual can be written as now the inf over functions phi. It'll turn out if you go track everything, it will still be an L1 mu function. Plus the integral of phi star d nu. And that's about it. There's no, as I remarked before, when you do the C transform, you automatically satisfy all the constraints. So this is a equivalent modified dual program, right? So this is sometimes called this optimal transport semi-dual. So it's like some sort of partially optimized dual that we have. Okay, so, and maybe I will now tell you a fact. I will not prove it. It's not very difficult to prove, but take some effort, which is I promised you at the beginning somewhere that there are some relationships between primal and dual objects. So in the case where, so if you satisfy the conditions of Praneeth's theorem, then you can prove, and that's why we labeled it phi here, that the optimizer of this thing is in fact the same, where phi 0 is the minimizer of the dual program. Okay, so you have to now remember back to Brennier's theorem. It promised you that there was some convex function that that optimizes, that whose gradient is the optimal transport map. And here we're saying, okay, that convex function you can also have recovered by solving this dual program. And so we're now saying again, the one part is easy to see, that the optimizer of this program will always be a convex function. You just do the C conjugate trick a few times. So the convex conjugate of any function is a convex function, differential conjugate. So you know that these functions, the phi that optimizes it, there is a convex phi that optimizes it. And you can take that phi and take its gradient, it'll give you back the OT map. Okay, so this is maybe the main thing that one can get out of duality for W2, which is you can instead get that you can solve the semi-dual program if you want, and from it obtain an P0, which is in fact related to the optimal transport map. Okay, so let me pause here.
This should be true. Like, so why should T0 be the gradient of the optimal? Is there like some way to see this?
I mean, yeah, there is, but it's a bit difficult to write it out fully. So, I mean, it is a consequence of the sort of the Fenchel equality, which will tell you something. So, I mean, okay, I don't know if it's not very easy to prove it fully, but there's some fact that you know that phi of x plus phi star of grad phi of x will be equal to, I don't know,
Yeah.
x transpose grad phi of x. So
Oh, I see.
you
Yeah.
use, so somehow it is the function that saturates. So phi and phi star will be so if you put phi 0 and phi 0
Yeah, now I see.
star, it'll saturate all your constraints and it'll maximize this thing
Yeah,
appropriately.
yeah, great. Thanks.
So in that dual formulation inside the box,
Mhm.
can we like have the infimum overall convex phase? Like
Yeah, it's equivalent. That is, if you, so you can add the constraint that phi is convex. And again, the way to see this is that if I start with a phi, and I look at its conjugate phi star, that will be a convex function. And then I can again take the conjugate of that and so I can replace it by phi star star. And so you can see that there is an optimizer of this that there is always a convex optimizer of this. So yes, you can add this constraint that phi is convex.
So can we prove its uniqueness?
For the quadratic, yeah, for the quadratic cost out of, yes, you can prove that there is a single convex maximizer. So somehow, yes, for the quadratic cost under the conditions of Brenner's theorem, there is a unique optimizer. I will prove a version of this which is even stronger, which is that the minimizer has some stability. At some point, it'll be useful for us to know that, and I'll prove something like that under some stronger conditions. So it's not always unique. Under the conditions of Brenner's theorem, it is unique, and under some stronger conditions, it'll also be stable in some way.
Thanks. I think we can continue.
Okay, so I guess how much time do we have left?
We have
About 15 minutes?
I think we have more because it's title late. So we have 25 minutes.
Okay, so let me start off with now. Okay, so we've sort of understood maybe a little bit of the structure of the OT program, and we've seen that it has various nice connections to convex analysis in the L2 squared case and so on. And now I will change gears and we will start talking about what the setup is for statistical optimal transport and what are the questions that maybe one might want to answer in this setting. Okay, so far everything we've talked about just assumes that you have access to these distributions mu and nu, and then you say, okay, what does the optimal transport map look like? Maybe in practice, when you want to use these, maybe you're going to apply it to some data. And then maybe the question that you want to ask, or one of the questions that you might care about is, how well can you estimate all of these objects from data? And so, okay, the setting that we'll work in is something like this. We'll typically say mu and nu are not known to you. But instead, what you have is sample access to them. So that means I will give you a collection of random variables that are drawn from each of these distributions. And okay, for simplicity, I'll assume that I give you n samples from mu and n samples from nu. Right, so this is the setting of statistical optimal transport. And now the question is just, how well can I estimate various things? So what are reasonable or interesting things to try to estimate? I'll list a few now. So maybe so we will typically make the assumption that mu is, say, absolutely continuous. Then it makes sense, as we've seen, to ask, okay, can you estimate the optimal transport map? So what does that mean? I want to take in these samples, x1 through xn and y1 through yn, and construct some estimate t hat that is hopefully close in some sense to t0. And the questions that we might care about are, okay, how many samples do I need to do this reliably?
Shiva, can you illustrate cases where this map would be good to know?
You mean why do I want to know what the map is?
That's right. Where is it used?
Yeah. Good. So maybe it'll be a little bit of detour. Yeah. So okay. So yeah. So I don't know. Yeah, I'll give you vague examples and then concrete examples. So let me do that. So this will be a slightly long answer to your question. So maybe the most classical one is something like generative modeling. And so by classical, I mean standard. So here is a setting that I might care about. I give you x's, they're drawn from some some distribution that I like, that I can sample from easily. And then I hand you some samples, let's say y1 through yn, and these are real images. So these are real images. Potentially this is a setting that you can think about. And so the question I'm asking is, how do I transform from noise and obtain samples of images, of real images? So this is roughly under the hood, the task that one is trying to solve in some sense. When you think of something like a diffusion model, they're not exactly solving an optimal transport program. So they are, though, solving some sort of transport problem. And so this is one application, which is it's just okay. Yeah. If you can try, if you have a map that transforms, say, a noisy a sample from noise into a real image, this will, in some sense, be a useful generative model. You can try to do useful things with it. This is one. Maybe a more. There are many, but let me tell you a different one. This is so. Okay, this is called I don't know, it's called Waddington OT. And this is a case. Okay, so this is a general sort of type of application that comes up in statistics, which is you should think of some sort of imaging technology. You're using something like single cell to make measurements of some type. And so maybe you're making gene expression measurements, or you're measuring the concentration of different cells in some tissue. And you do it at various time points. So let's say I take at t equals 0, I make some measurement of, I don't know how, okay, so I take a tissue, I slice it up, and I say, what are the different cell concentrations at t equals 0? And then I do the same thing, but I can't, I would like to track what happens over time, but I don't have a way to, so once I whatever, slice this tissue to get cell concentrations at time 0, I kill the tissue. So I can't actually track what's going on over time, but I can take another different sample and measure the cell concentrations at a different time point. Right? So it's just that these, and so what I've done is, in effect, I cannot track the distribution through time. But what I can do is take a measurement at time equals 0, at time equals 1, and so on. So I've somehow broken the correspondence between my samples. So these are called broken correspondence samples. And this happens frequently in applications. And then you can say, okay, well, I would like to recover this correspondence. I would like to say which cell went where. And there isn't a way to do this, but maybe you can say, suppose I sample at time points that are sufficiently close. Okay, then some sort of OT matching between them should be the right way. There's like some physical reason why maybe they didn't do something super suboptimal. That is, if I can somehow match the sample at time equals 1 or 0 to time at time epsilon and so on, then I can recover this correspondence. And so maybe the high level is, okay, there are lots of these broken sample problems, and then the OT map is a canonical way to recover this correspondence. I don't know if that helped.
No, that's very nice. Thanks.
Okay. Yeah, I didn't want to make this deviation right now, but okay. The high level, it's if you have samples which don't have a correspondence, but you would like a canonical way to define one and then study stuff related to it, then OT does give you such a way. So that's a case where you would actually care about recovering the transport map. Okay, so let's back up. Oh yeah, okay. So yeah, so this is maybe one question that one might care about. A different one that one might care about. So that is the first canonical class of problems. I give you samples from the distributions and say, what is the OT map between them? The other thing that I might care about is to estimate the Wasserstein distance between them. Something like W2 squared between mu and nu, or maybe W1. Right? Once again, I don't give you the two distributions. I just give you samples from them. And this will come up if you are trying to do something like hypothesis testing. So this is a way to do hypothesis testing. So as a canonical example, maybe I'm going to give you samples from mu and nu, and maybe I want to solve what's called a two-sample test. So a two-sample test is, did they come from the same distribution or not? So I want to test the null hypothesis that mu is equal to nu, and I want to test it maybe against alternatives. Under the alternatives, say some WP distance between them is large. Right, so if I'm trying to distinguish these two alternatives, so in one case, they're actually from the same distribution versus they're far away in the WP distance, then a reasonable thing to do would be to try to estimate this distance and then base your test on that. Okay, so a different question you can ask is, okay, given samples, can I estimate the Wasserstein distance between the underlying distributions?
Quick question.
Yeah.
Is WP a metric? Or so, for example, you've written W2 square here. So is the metric W2 or is it W2 square?
W2 is the metric. W2 squared is just a convenient thing to estimate somehow. But yeah, W2 is the metric.
Thanks.
Okay, great. The other thing that you could try to do is maybe density estimation. So what's the question here? I give you samples from, let's say there's just one distribution now. I give you samples from mu, and I want you to solve the following problem, which is construct an estimate mu hat so that its OT distance to mu is small, right? So that the, let's say, WP distance between mu hat and mu is small. And again, you can ask, okay, how many samples do I need? And so on. So you can ask about the sample complexity of this task. So all of these are statistical optimal transport problems where the basic premise is, instead of giving you the distributions, I give you samples from the distributions. Let me also just briefly mention one other thing, which is, so I didn't really touch a lot on this, but one reason why
I have a question. So
Yeah.
this is regarding point 3, where you say that you should construct a measure so that the Wasserstein distance is small. Is there any reason to believe that mu hat is not just the empirical estimator? Because you have a Wasserstein law of large numbers, right? Which gives you an n to the minus 1/3 convergence.
In 1D, maybe something like what you said is correct. But yeah, so yeah, so okay, so let me just remark. So yeah, maybe mu n is, so the empirical measure mu n is a good or good enough. So, and yes, indeed, this is one of the reasons why people like optimal transport, which is if I wanted to estimate a distribution in KL or TV, I inevitably have to make some smoothness assumption on the distribution, and I have to construct an estimator based on some sort of kernel smoothing or something like that, and those are maybe impractical. One thing that's nice about the Wasserstein distance is that it's a smooth distance in its own right, so you don't need to make any assumptions. As long as you make some moment assumptions, the empirical measure will consistently estimate the Wasserstein, the true measure in the Wasserstein distance. But maybe you can do better. For instance, if the measure is in fact smooth, you can do better than the empirical measure. So we might revisit this at some point. Good?
Yeah, good.
Okay. Right. So the other thing, and I didn't talk about this much, is that people often like the OT/Wasserstein framework because it has some sort of shape preserving property. So I will not, I will just tell you roughly what this means. That is, okay, so let's first say, what do I mean by barycenter? I'm going to give you a collection of distributions now. So mu1 through mu k. And I want you to, so these are distributions, and I want you to say, what is the average of these distributions? I would like some sensible notion of average of these distributions. So one way to define it is to define what's called the barycenter, which is exactly this object. So you put your favorite WP distance here, and you say, okay, so maybe find the thing that is closest on average to all of the distributions that I handed you. Right? So this is the barycenter. You can define it given any metric. You can define a metric barycenter in this way. And so now you can say, okay, the statistical OT question would be, if I gave you samples from these distributions, how well can you estimate the barycenter? And let me just remark quickly, why do people like the Wasserstein barycenter? So this is this claim that it has some shape preserving property. There are pictures that illustrate this, but maybe I will just tell you a simple example that will help a little bit. So suppose I think about I just take two distributions and I say, what is their Wasserstein midpoint? So, or what is their average? So I give you mu1 and mu2. And let's for a second just imagine that mu1 is this distribution. It's a Gaussian with some mean. And let's say mu2 is another Gaussian with a different mean. It can have different covariance as well, but let's think about this, right? So let's say this is some normal with some mean and some covariance, but let's say it's the identity, and this is a normal with some other mean and some, right? So suppose I took these two distributions and said, what does their average look like, where I say their Euclidean average. Their Euclidean average, so the naive average, would be the mixture distribution, right? So one definition of average, maybe, of their midpoint would be the mixture, which is this distribution. So it's a mixture of two Gaussians, right? So this is one definition. This is not the Wasserstein midpoint. On the other hand, the Wasserstein midpoint will turn out to be a Gaussian somewhere in the middle. It will also be a normal with some mean, I guess in this case, it might actually be right in the middle. So you can define, and so what does this mean? You can imagine trying to take these two distributions and constructing a path between them. So if I want to go from one Gaussian to the other, the Euclidean average way, the usual mixture way of doing it, will sort of start, I don't know, increasing one of them until it reaches and decreasing the other, right? So if I want to go from the first distribution to the other, I'll kill off the first distribution, but all the things in between will be mixtures of Gaussians. The Wasserstein path between them will, in fact, just take the first Gaussian and move it over slowly to the second Gaussian, right? So there's some sense in which some of these Wasserstein operations preserve the shape of the distribution, and that's one of the reasons why people like it. Okay.
How does P play a role here in the Wasserstein distance in this picture?
You mean if I change WP to something else?
That's right, yeah.
Yeah, so there's some closed form expression for these. For Gaussians, actually, I'm not sure I know the answer. So maybe, okay, you should just think of the case with W2 looks like what I said. I'm actually not sure I know the closed form answer in general. Yeah, I don't know exactly what it does. So let me just write it this way. There might be a closed form expression for WP in general for between Gaussians, and then it'll tell you what role P plays in this thing. It might be the same always.
Okay, thanks.
Yep. Okay, good. All right, so let's go back to the statistical OT setting. So I'm going to start talking about the first one, which is how do I estimate the transport map, and then in the next two lectures, we will talk a little bit about some of this density estimation task, and as a consequence, we'll get results. So we'll talk about problems 1, 2, and 3. We'll start off with problem 1, though. Okay, so today I will just tell you a little bit about how people estimate the OT map. And then in the next lecture, we'll talk about how one will analyze it. Okay. All right. So okay, so the first question maybe should be, how does one construct an estimator of the OT map? What are sensible principles by which one can do this? And there are two that are very common. One of them, I'll call them dual estimators, and the other are primal estimators. Okay, so dual estimators, again, will make various regularity assumptions at some point, but we just want to say, given samples from the two distributions, how do you construct any reasonable estimate of the OT map outside of those sample points, for instance? Okay, so what is the dual principle? Remember that we derived some fact today, or at least we stated it. We said under some conditions, P0 does look like this. There is a so-called, okay, this thing will be called the Brenier potential. It's the argmin of phi d mu plus p star d nu over phi, which is convex, say, or phi is in some nice class of functions. At least it should be L1 mu and convex, can be convex. Okay, so you can imagine trying to construct estimators by saying, okay, this, if I could solve this problem, if I knew mu and nu, I would solve this problem, I would get phi 0, and I would construct T0 by saying, I'll take the gradient of this convex function. Now, if you stare at this expression, it should remind you of something. It's like a standard problem in machine learning, which is like empirical risk minimization, right? So it is the minimization over some collection of functions of some expected value, right? So these are two expected values. So the natural thing to do is so you want to solve this population risk minimization problem. So the standard thing maybe would be to do, this is the ERM principle, or the empirical loss or risk minimization principle. And so it will say, sorry, what was the question?
No question. I was just saying that, I guess this is where the stability of the minimum matters.
Yes, precisely. So to reason about it, one will need such things, but let's for now just try to define an estimator. So you can say, I'm going to define my estimator by saying minimize over phi in some function class phi of the integral of phi d mu n. So this is, I'm just going to take the average plus the integral of phi star d nu n. Right, so where mu n is the empirical measure, and nu n is also an empirical measure. Okay, so let's forget for a second how one might do this, but this is a reasonable way to define an estimator, and then I would define an estimator of the map as the gradient, say, of phi hat. Hopefully it's a differentiable thing, and I can just define this. And without saying any more, one can say, okay, can I analyze this estimator for somehow reasonable choices of this function class? And we'll get to some things of this form. But maybe let me also say, in practice, this is one of the dominant ways that people do it. So in practice, people, so this is maybe originally comes from this paper by, so they used, I don't know when it was, maybe 2020. They used, you parameterize this function class by neural networks, and you particularly want to ensure that the neural network outputs convex functions. So there is something called input convex neural networks. So you should think of this. Okay, so this is by Amos et al. This is just a way of defining neural networks so you parameterize a neural network, but ensure that the function that the neural network is producing is always convex. So it has the same structure as a standard neural network. It's deep, it has nonlinearities, but the guarantee is that whatever the function that you are parameterizing is always convex. And so you can take this class of neural networks and then try to do some sort of standard SGD-like thing. You have to be a little careful because there's a convex conjugate sitting in here, but you can also write out the convex conjugate itself is an optimization problem. So you can try to do this bi-level optimization over the class of input convex neural networks, and this will produce for you something, and then hopefully it's differentiable. And in practice, this is one of the dominant ways that people estimate OT maps. Okay, let me pause for a second and see if there are questions, and then otherwise I'll tell you a little bit about primal estimators.
The primal thing, because we are short on time.
Okay. Or should I, maybe I can start with the primal thing in the next lecture. That's, well, anyway, I have to recap it. So,
I just had one question. So earlier we talked about if you have any valid transport under the conditions of Bernier's theorem, then Brenner's theorem, sorry, you see that if you can figure out the mass preserving element, you get an OT, right? Now, you also gave this example of diffusion models where you can go from N to the data distribution. So is it that finding this mass preserving element is the hard part here? Or else you could take a diffusion model and just find the OT?
so what you're saying is correct, that it is not a constructive way of coming up with it. It's not necessarily easy to compute this polar factorization of a given map. But in some spirit, that is what things that straighten the flow. So if you think about, I don't know, if you've ever heard of rectified flow, you can look this up. So it is a way of trying to so iteratively refine a transport map to be straighter, which is somehow bringing it closer to the optimal transport map. So there are algorithms that people have come up with which try to do roughly what you said, which is you construct some sort of diffusion map, which is maybe a suboptimal map, and then you try to refine it to get closer to the OT map.
I see. Thank you.
So I have one question. So in these examples that you gave, especially with the one about generative modeling, and there seems to be some intuitive understanding that the OT map is the correct one. But like, you know, I mean, why should the diffusion take the diffusion you want? I mean, why should it take the shortest path? It could take some long path, and maybe that's the right one.
Yeah, so this is true. So in generative modeling, for instance, there is no canonical reason why one should think the OT map is the thing that you're going after. In fact, arguably, if the OT map is very hard to estimate from data, but I can give you some suboptimal map that is much easier to estimate from data, then it is certainly the case that one should. So somewhere you also should care about how hard these objects are to estimate. But maybe in principle, if you could estimate it, it seems like a very reasonable target. It is something that solves this and is well defined. If you cannot estimate it, then yeah, and this is maybe why the whole generative modeling, diffusion models literature exists, right? Like the OT map is not that easy to estimate from samples. So, and there is no reason why you should want it if your only goal is generative modeling.
Also, maybe one more stupid question. So, do you know of any connections to physics? Because some physics says this whole thing about principle of least action. So, is there any connection between OT and that?
Yeah. So underlying, for instance, is Waddington OT. There is some principle of least action. There is also I don't know, Schrodinger in the 1930s defined a version of optimal transport, which is called entropic optimal transport. But he was after some physics thing where, I don't know, he's thinking of hypothetically this problem where I look at the gas concentration at time t equals 0, and then I look at it a little bit after, and now I want to understand what happened to the molecule. So it's exactly like this Waddington OT, but there's some noise in it. So so he was constructing some variant of OT where you also allow for
Bridge
noise
problem.
and
The bridge
to
problem,
be the bridge problem exactly. So Yeah, so there are lots of physics problems where I can try to recover correspondences, and maybe I'm going to say, okay, maybe there's some Brownian motion underneath, then I will recover some regularized version of OT.